Temperature expansion. Before we go into the theory and how it all would work with your calculations and so, let's have a look at a scenario that might, an analogy that would be able to give you a better understanding of how thermal and temperature expansion would work, as well as look at an example and a demonstration of how different materials expand as temperature increases. Let's consider this mini bus. So this is a mini bus that we tested, that we made remote controlled, and we tried to let it roll over, which we weren't too successful on with it, because it was actually, the design specs were correct. It was serviced, it was new, there were no problems with it, so we weren't able to roll it. Nonetheless, let's say you're in one of these mini buses, and these mini buses are filled up completely with passengers. So the maximum number of passengers legally allowed would be, let's say, 15 people. Okay, so it's a normal day, it's early morning, and you filled up, there's 15 people in this mini bus, and it starts getting hot, and it's one of those really hot days, and it really gets to like 40 degrees, 45 degrees Celsius. As this temperature increases and you've got 15 people inside of this vehicle, windows are closed, the air conditioner is not working, you're going to start getting stressful. You're probably going to be starting pushing each other with your elbows, almost like a chicken wing scenario. And the tension is going to get really high over there. You're going to get irritated, and the stress levels of everybody is going to increase. Okay, so the same scenario can be considered. Let's say now you are filled up on a normal day. It's in the morning, you fill up the minibus with 15 people, and you're sitting comfortably over there. And then the temperature starts decreasing. It gets really cold. It gets to like 5 degrees Celsius suddenly. And in this specific case, the windows might be open. You might find that the cold air is flowing into the vehicle. And so now it's getting like really cold. So now your stresses are going to be decreasing. You probably going to start snuggling up next to each other to try and share body warmth, and to be able to get more comfortable. And you probably will find that you might be able to get more than 15 people in a vehicle, because everybody's snuggling up. It obviously won't be legal, but people will be willing to have still extra few people into the vehicle, because they're snuggling up, there's more space available, and you know, there won't be as many stresses or tension if people are sitting next to each other. And so, in a very similar fashion and way, we can associate this with temperature stresses, temperature expansion, and also contraction, if you look in that way. I've got two pieces of copper over here. The one on the left hand side is secured on either end, and that one is measured to be 66.28 millimeters. So let's just verify it over there. Okay, so 66.25 millimeters, and the smaller one over here is secured only in the center, and I've actually marked it around it over there, and that is 43.54 millimeters. Okay, so now I'm going to heat it up, and we're going to see how it expands and what it does. Okay, so for this one, where it was secured on either end, as it heated up, you can see the tape lifting up over there as it expanded, because it didn't have anywhere to go. So there was forces in the and stresses in the material, which caused it to then lift up over there. And you can see as it's starting to cool down, it will then start lowering back to be flat with the surface over there. We heat up the same, this piece over here secured in the center, and see how that would Okay, you might not see the expansion over there, but we'll be able to measure it. Okay, so according to this, it's 43.8 millimeters in length after we heated it up. And you might have seen that it went across the lines that we actually had over there that was outlining that piece of material. As you can see over here, this piece of copper has now cooled down. It's flat with the surface and it hasn't folded up due to the increase in thermal expansion. Okay, so let's start with linear expansion. So as with the example that we've done, when you look at this piece of material and it expands in and out depending on the temperature and the heat on it, that's known as linear expansion. Okay, so there's a few formulas that you need to be aware of that are important to know. So specifically for linear expansion, the first one we're looking at is delta L is equal to the original length. Okay, so the change in length is equal to the original length multiplied by alpha multiplied by delta t. Okay, so alpha is a coefficient of linear expansion. That's a value that is a constant value for each different type of materials, and this is given to you. And then delta t is a change in temperature. The final length, obviously that will be original length plus the change in length. Okay, so this is your basic equations that you're going to be using for linear expansion. Now when it comes to area expansion, you will notice that it's very similar in the type of equations. So with area expansion, you've got a change in area is equal to the original area multiplied by beta multiplied by delta t. Okay, so it looks very similar to the the linear expansion equations. The only difference is that it's now change in area instead of just change in length. And we've got beta instead of alpha. Beta is a coefficient of area expansion. Beta has got a value that's roughly equal to 2 times alpha. It's not like 100% accurate, but it's a good estimation for calculations and to do the sort of calculations and to do the estimations that you need to do. So we always use beta to be twice of alpha. Okay, obviously the final area is equal to the original area plus the change in area, because that's area expansion. So we've basically looked at it in terms of a one-dimensional system. We've looked at it now in a two-dimensional system. Now we need to look at it in a three-dimensional system, and that's with volume expansion. Volume expansion is again very much similar to what we've looked at in area expansion. So change in volume is equal to the original volume multiplied by gamma multiplied by delta t. So again, our only difference is we're looking at a change in volume and original volumes. We've got variable gamma, which is now not beta or alpha anymore. And gamma is a coefficient of volume expansion, and it is roughly equal to 3 times alpha. Again, it's not exactly accurate, but it's good enough estimation for the calculations that we need to do. Obviously, your final volume is equal to the original volume plus the change in volume. Okay, and then finally we're looking at temperature stresses, which is also some equations you just need to be familiar with. So obviously we know that delta L is equal to stress times the original length over E. We also know that delta L is equal to the original length multiplied by alpha multiplied by delta t, which we've just looked in terms of linear expansion. So therefore we can say that stress is equal to alpha delta te, and that's just by making these two formulas equal to each other. You keep in mind this equation is for a rigidly fixed ends type of scenario. If we have got a situation that there might be space between our materials as they expand, then we need to take that space into account, and that's where we come with the equation of stress multiplied by length over E is equal to the length multiplied by alpha
multiplied by delta T minus the allowance. The allowance is that space that I was referring to where some expansion can then occur. Okay, so with this linear expansion, it is quite critical to take into account. This is sort of the scenario that you would come across when like for example with power lines. Often you would see power line cables going and they are sort of going and hanging with some ability to be able to move a little bit, and the thing is you don't want to make those cables too tight, because if it gets colder there's going to be contraction and that's going to cause tension on the cables. So they're able to hang a little bit, and so that there's some ability for expansion and contraction of the material. So those type of things need to be taken into account whenever you're doing your designs. It might be just a normal electrical cable that's going somewhere, but if there's temperature expansion and contraction happening, it could cause it to snap, and you don't want that to happen. So temperature expansion is quite important to keep in mind. Okay, so let's have a look at example. So we've got a sphere and it is a volume of 1 cubic meter. The temperature increases by 60 degrees Celsius. The linear expansion coefficient is 17 times 10 to the minus 6 per degree Celsius. First thing we've got to do is, what is the increase in volume? Okay, so before we do that, the first thing we're going to be doing is we're going to say, well, gamma is equal to 3 times alpha. And we know that is then, if we do that calculation, 3 times 17 times 10 to the minus 6, we get 51 times 10 to the minus 6 per degree Celsius. Okay, so now we've got to calculate the change in volume. So therefore, the change in volume, or delta V, is equal to gamma times original voltage times delta T. Okay, so that is equal to 51 times 10 to the minus 6 multiplied by the original volume is 1 cubic meter multiplied by 60. So we told the temperature increases by 60, and so therefore we don't need to have original or initial temperature and a final temperature. We know it's going to be going up by 60, so we just use 60 over here. Okay, so once we've done that, that is then equal to 3,06 times 10 to the minus 3 cubic meters. Okay, so what is the final volume? Well, the final volume, we know that the final volume is equal to the original volume plus the change in volume. Okay, so that is equal to 1, which was 1 cubic meter, that was the original volume, plus the change in volume, which we've got over here. Okay, and that is equal to 3.06 times 10 to the minus 3. Okay, and the final value for this is equal to 1.00306 cubic meters. Okay, now that we've done that, what's the final diameter? So obviously if this sphere should be expanding, the diameter would be expanding. And so it becomes quite an interesting scenario. Okay, so if we look at a sphere, the volume of the sphere is calculated by pi over 6 multiplied by the diameter cubed. Okay, so therefore we know what the volume is. We've calculated that, so at least what the final volume is. So that is 1.00306 is equal to pi over 6 multiplied by d cubed. Okay, so all that we've got to do now is we've got to make d cubed a subject of the formula, and then we've got to take the cube root of it. Okay, and when you do that, we find that d is equal to 1.242 meters. Okay, So that is the sort of way that you would go about when you've got some expansion in temperature, and in this case it's a sphere. We looked at a more complex scenario, but the same type of scenario would happen for area or even in a linear fashion. Okay, so let's have a look at an example where we've got an aluminium rod, and this aluminium rod is 320 millimeters long, and this is at a temperature of 120 degrees Celsius. And it has a diameter, this specific rod has got a diameter of 15 millimeters. The ends are rigidly secured. We are told that E for aluminium is 70 gigapascal. We're told that alpha for aluminium is 23 times 10 to the minus 6 per degree Celsius. And then we get told the rod is cooled down to 20 degrees Celsius. What is the stress? Okay, so keep in mind we've got essentially a rod as such. This rod is at 120 degrees. We know that it is rigidly secured. Okay, so it could be connected to some wall, for example, and cannot move. We know it's 320 millimeters in length. Okay, so this is at 120 degrees Celsius. Okay, and we know that the diameter of this is equal to 15 millimeters. Okay, so we've got, now when it cools down, there's going to be contraction happening, but because it's secure over there, there's going to be some stresses acting on it. It's going to be pulling from these walls, and so there will be stresses. Okay, so if you recall correctly, we've got a formula that stress is equal to alpha multiplied by delta T multiplied by E. Okay, and so that's equal to alpha over here. We are told that is equal to 23 times 10 to the minus 6, sorry. So 23 times 10 to the minus 6. The change in temperature, well, that is equal to 120 minus 20 degrees. Okay, so multiply by 120 minus 20 degrees, and then we multiply that by E, which is 70 gigapascal. Right, okay, and then when we do this calculation, we find that's equal to 161 megapascal. That will be the stresses acting on it. Interesting though is that we can see that from this equation that the length of the piece of material doesn't really affect the stresses. Okay, the length doesn't come into the equation, so we didn't even have to be told what the length of the rod is. Okay, so we've had to look at an example of stresses being used for well, temperature stresses that there might be. We've also had to look at how the expansion of temperatures happen. In this specific case, we looked at a sphere, and then we had to look at the basic formulas. So keep in mind that when you look at the basic formulas over here, we've got linear expansion, air expansion, and volume expansion. All three of them are pretty much the same equation. The only difference is with linear we're using alpha, with air we're using beta, and we're using gamma when it comes to volume.